All right, here's a just a quick little scribble cast. Well, hopefully it'll be quick on geometric series and sequences. So in this section, what we want to do is look for common ratios, finding general terms, look for a specific term perhaps, find the sum of a series. We'll maybe touch on this fractional notation for decimals, and also look for some applied problems. So, when we're looking at geometric series, we need to understand what geometric is versus arithmetic. Here's an example that illustrates both. So here's summer jobs. Which one would you take? Would you be a Lucerne driver, 20 bucks an hour for 40 weeks, or for 40 hours a week, and the job goes May, June, July, and August? Okay, you could probably figure out how much money that would be. So you could take that job, or you could be a farm laborer. You get a penny for the first day, and then your wage doubles every day after that. So you'd get a penny the first day, and then you'd get 2 cents the next day, and 4 cents, 8 cents, etc. So which job would you take? And it's maybe a contrived question, but we'll see later in the Scribblecast how much you'll get for this one. Anyway, this is an example where here your wage just increases, or how much money you get just increases per hour that you make. So if you work 1 hour, you get 20 bucks. You work 2 hours, you get 40. You work 3 hours, you get 60. And notice that the difference between those, or that there is a common difference. So there's a common difference of 20. This one here would be known as an arithmetic sequence or arithmetic series. Geometric is where when you look from one to the other, notice that there's a common difference here of 1 cent, but then here it's 2 cents, and then here it's 4 cents. So there's not really a common difference at all. But maybe you could look at something else that's common. And here if they say double your wage, you can see, oh, every time I go from one term to another term, I'm doubling it. So I'm timesing it by 2. And that's known as a geometric sequence or a geometric series. One thing that is common in all geometric series is that they have that thing that was changing here, it was doubling, is known as a common ratio. So you know you have a geometric sequence or series when you have a common ratio. So just take a second and see what the ratio for this one would be. You might already see that the ratio there would be 3. Here, ratio may be a bit harder to see, but this looks just like the one that I just did, right? Looks like I'm timesing by 2 each time, and so I think the ratio will be 2. If you're not quite sure, what you can do is just use this formula. And this formula says the ratio is equal to any term, let's say pick this term. So that would be 0.04, and that's the third term, so this n here would be 3. And divide that by 3 minus 1, so 3 take 1 was 2, so that I have to divide that by the second term, or the previous term, which is 0.02. And if you do that division, sure enough, you'll come out to a ratio of 2. So geometric series or sequences are known if they have a common ratio. And every term in that sequence has to have that common ratio. So here's some. You can, if you want, pause, and you can see if you can determine what the ratio on these are, and hit play again once you think you've got them all. Common ratio for this one would be 2. Common ratio for this one, careful with this one, there is a sort of a factor of 3 happening, right? But you're going down, and so really a ratio is what you multiply this one by to get this one. So in this case, the ratio would have to be a third. This next one, we can have negative ratios, so it'd be a -4. And this last one, I believe, you multiply each term again by a third, and you'd get the next term. Okay, so that's figuring out ratios. Now, with the geometric sequence or series, if I want to find out a specific term, sometimes it's nice to have a formula. And here's a formula that represents a geometric sequence. AN specifies a specific term. Like I could have A6, that would be the 6th term. Or A12, that would be the 12th term. If I say an, I'm just saying, well, it's a term, some term, I'm not sure which one, until I guess I know what n is. A1 stands for the first term in your sequence. R, of course, stands for the ratio, and n stands for how many terms you have. So let's try this maybe with a question. So here it says I have a sequence 1, 2, 4, 8, and it goes all the way up to 1024. And I guess maybe it could keep going, but they want me to know what the 8th term is. So I'm going to put an 8 in everywhere I see an n. So A8, I don't know, is equal to A1, that's 1, times the ratio's 2, to the n is 8, so 8 take away 1. So 1 times anything won't change it, so the 8th term will be equal to whatever 2 to the 7th is. So 2, 4, 8. I gotta figure this out. I should grab a calculator. 2, 4, 8, 16, 32, 64. Am I there yet? No, one more. 128. So the 8th term will be 128. Okay? Let's try a couple more. Oh, I had some people down to do these, but if you wanted to, pause and see if you can use the term formula here to determine what the 7th term in each of these sequences are. Okay, hopefully you're back. So I would say A7 is equal to the first term is 2 times the ratio, looks to be -3 to the 7 minus 1. Or 2 times -3 to the 6th. One thing to be careful here is that you have to remember you're using BEDMAS, always, that's part of the game. Nothing in brackets, but exponent is next, so you have to raise -3 to the 6th power first before you multiply it by 2. So don't go 2 times, so this is not equal to 2 times a -3 all raised to the 6th. That's not correct. You don't want to do that. You've got to take -3, raise it to the 6th. That'd be I don't know, 729 or something, and then times that by 2. Okay. All right. This one down here, same kind of thing. A 7th term is equal to the first term is √2 times a ratio. Oh, maybe I better figure out what the ratio is over here. I'm going to take this term. So 2√2 divided by the one before, a 2. So these 2's here would cancel. So my ratio is √2. Okay, R is √2. Raised to the 7, take away 1. Okay, so this would be √2 times √2 to the 6th. Again, I need to figure out what this is, √2 to the 6th. You could do that on your calculator if you wanted to. I think it comes out to 8. So it'd be √2 times 8. Or typically we write the integer out front there. Okay. All right. Now one thing. I guess let's try this question. This is the one that I introduced the class with, and it is: if you earn a penny a day, double your wage, how much are you going to make on the 30th day? So the 30th day would be A30 is equal to A1. That's a penny. Times the ratio, I'm doubling every day, so it'll be a 2, to the n is 30, so 30 take away 1 is 29. So now if you go and do this on your calculator, you're going to come up with however much money you'll make just on the 30th day. Not all the days, just the 30th day. And you'll find it'd be 5 million and something. So it's quite a large number. I think I'm just going to pause for a second to figure out what that number is. So 5, 3, 6, 8, 709 and 12 cents. So that's how much money you would make on the 30th day. That's quite a bit of coin. Okay. Now sometimes with geometric or arithmetic sequence in series, it's nice to know what a general term is for a particular situation. And a general term would be an expression, I guess an expression or an equation that shows you everything that's there except for one of the variables. And in sequences, typically we don't plug in a number for n. So for example, if I have this sequence right here, I notice that the ratio is 3 and the first term is 2. So I could write a general term using this formula, an equals a1 r to the n minus 1. And what I do is I plug in everything I know except for what n is. And that'll be my general term. So an equals first term, that's a 2, times the ratio, that's a 3, to the n minus 1. So this here would be known as the general term. And the nice thing with the general term is that as long as it applies to the situation you're looking at, you've got everything set up, so now all you have to do if you wanted to know, say, what the 20th term would be, all you'd have to do, you wouldn't have to think about the first term or the ratio or anything. All you'd have to do is plug in your numbers, put it in your calculator, and away you go, you're done. Okay, so that's a general term. Here's a question that is an interesting one to try and figure out. What we've got here is we have two situations. I've got a sequence, so I've got a bunch of numbers, and I know the 7th term is 192, the 12th term is 6144, and what I'm asked to do is to figure out what the first, the different, or not the difference, the ratio, and what the first 5 terms would be. And then they ask us to find the general term. It's an interesting question. To solve that, we use system of equations, sort of a variation of that. It's basically substitution, but so to solve it, what I do is I put a 192 in for A7. So A7, I know what that is. I'll put a 192. First term, I don't know. Ratio, I don't know that either. And then n is 7, so 7 minus 1 is 6. So there I've got a formula that relates this point. Okay, let's do this next one. So it'd be 6144 is equal to, don't know the first term or the ratio, but it's a 12th term, so 12 take away 1 is 11. And then I can perform a system of equations on this thing. And it might look a little bit funny, but this is a sort of a slick way to do it. You could write this one, let's go 6144 equals a1 r to the 11. And you could divide that by 192 equals a1 r to the 6th. So when you divide these, and I know it looks a little bit odd, but I'll go 6144 divide 192. That gives me 32. So this divided by this is 32. A1 divide A1 cancels. And then r to the 11 divide r6, common basis, subtract the exponents, you get 5. Now you can take the 5th root of each side and you'll find that r comes out to be 2. Once I know what r is, now I can plug it back into either this equation or this equation and solve for a1. That's a nice sort of tricky little question. Alright, let's turn our attention now to doing the same thing. So I'm looking again at a sequence of numbers like 2, 4, 8, 16, etc. But now rather than just looking at them as distinct numbers, what I'm looking for now is what I get when I add them up. So when you add up values of a geometric sequence, we now call that a series. So these that form a geometric pattern, if I'm adding them up, that's a geometric series. And again, I have a formula that I can use to determine what the sum of that series is. And there it is right there. So let's go back to that original question and say, well, how much money would I make if I made a penny at first day, double wage each day? And I want to know total how much I make the whole 30 days. I know on the 30th day I made 5 million and change, but how much would I have made for the whole month? So I can use this formula right here. The sum of 30 terms is equal to, first term, I was a penny, times by 1 minus the ratio, it was doubling all the time, and n is 30, all over 1 minus 2. So if you do that all in your calculator, you'll find, I think it's 10 million or something. Let me just try it quick here. 0.01 times brackets 1 minus 2 to the 30th, close a bracket, divided by -1. Oh, my number looks too high. I did something funny. Did I? Oh no, that's right. That's right. 10 million. Yep. So it's 10 million. I thought it said 18. 10,737,418 and 23 cents. Don't forget about the 23 cents. So that's how I could use a geometric series question. And there's probably lots of them. Here's a good example of one where you have to find the sum of this whole series. One of the problems that you'll have with this one is that when you go to find the sum, you won't know how many terms there is. So what you first have to do is figure out how many terms there are in this one. I'll maybe do that and then let you do the sum formula. So I need to know what term that is. So here's our formula for finding out terms. A1 r to the n minus 1. So now I know that this certain term is 1024 is equal to A1 as a 1 times the ratio looks to be a 2 again to the n, that's what I don't know, so n minus 1. So here I have an equation where I need to solve for n. It's up in the exponent, perfect time for logarithms, eh? So let's isolate this base with the exponent, so I need to divide both sides by 1. So I'll get this, and now in order to solve this I can use logarithms. We'll change this to log form. So it'd be n minus 1 is equal to log base 2 of 1024. So when you do log base 2 of 1024, I think that comes out to 10 if you use the change of base formula. So n minus 1 is equal to 10, therefore n is equal to 11. So this term here must be the 11th term of that particular series. Now, if they want to know what the sum is, so they're wanting to add all these terms up, now that I know it's the 11th term, I can plug that in there. I know the first term, I know what the ratio is, and I also know n is 11. I could plug it into the formula and determine that. Now sometimes with the geometric sums or geometric series, there are things that go on forever. For example, if you bungee jump, you jump from a certain height, like 100 meters, that'd be a good jump, and then you go down and then you rebound a certain distance or a certain ratio of the amount that you dropped. So like for example, if you fall back, or if you come back half the distance, and then you go back down and come back up half the distance. So there'd be a common ratio there. So for example, if I'm falling, I'd fall first 100 meters, come back up, and then I'd fall 50 meters, and then come back, and then I'd fall 25 meters, come back up, etc. And I would just keep dividing by 2 or multiplying by a half. That would be what my ratio is. Now, if a question says, how far will have they fallen before they come to rest? If they say come to rest, what they're indicating there is it's an infinite geometric series. It just goes on forever. And we have a little bit simpler formula if it's one that goes on forever. So in this particular question, they're saying how far will they have fallen each time. So they're not counting how much you bounce back, they're just counting how much you fall. So like here, I fall 100, then I fall 50, 25, etc. So this formula here will do that for me. So the sum of an infinite geometric series, first term, in our case, is 100, divided by 1 minus whatever the ratio is, and our ratio is a half. So if I simplify, that'll be 100 over a half, and 100 divided by a half is 200. So all told, by the time the guy comes to rest and they crane him down or pull him down to the river, whatever he's going to get down on, he'll have traveled downward, just downward, 100 meters. Here's another example, and it's the same kind of question where you drop from a height of 16, rebounds a quarter of the distance. Before it comes to rest, how far will it have fallen? Then again, you're going to be using that formula. One last thing with geometric series that we can do, and we can use this with arithmetic series as well, is that we have a short form notation to help us describe any kind of pattern where we're adding them up. So if it's a series where I want to add things up, this is a summation notation, it's called, in order to sort of simplify the question or write it in short form. And basically what it says is here is a general term for a specific sequence. And it says, here's our variable, this time is p, but it could be n or whatever we want. And what I need to do, how this describes a particular series, is what I do is I could plug in the number 1 in for p and figure out what I get. And then, well, let's do that. So 2 to the first would be 2. 2 times 3 is 6. So first term is 6. Let's do a couple. Put a 2 in. So 2 times 2 is 4, times 3 is 12. Plus. Notice what I'm doing here is I just keep plugging in the next number, and I keep going plugging in numbers until I reach 8. So I'm going to have to plug in 1, 2, 3, 4, 5, 6, 7, and 8. So let's do 3. So 2 to the third isn't 6. 2 to the third, 2 times 2 is 4 times is 8. And then 8 times 3 is 24. Now are you noticing a pattern here? Let's do one more just to confirm the pattern. I'm thinking the next number should be 48, but let's just confirm. So I plugged in a 1, a 2, a 3, now a 4. So 2 to the fourth is 16. 16 times 3, sure enough, 48. So this keeps going. And there will be 8 terms, because I'm starting at 1, going to 8, so there's going to be 8 terms. If I started a number other than 1, I have to sort of be careful, because this top number won't tell me how many terms there are. I'd have to sort of figure that out. But in this case, they're wanting to know what the sum is. So sum of a geometric series is equal to a1 times 1 minus r to the n all over 1 minus r. Now I'm going to plug in my a1 will be 6. It looks like the ratio is 2. I'll plug that in there. And n is how many terms there are. There are 8 terms. So I would just plug those numbers in, come up with my answer. Let me just do that quick. So the first term is 6. 1 minus the ratio is 2 to the 8th all over 1 minus 2. Okay, calculator time. Okay, calculator turn on. Okay, so I've got to go bracket 6 times, in brackets, 1 minus 2 to the 8th, close my brackets, divided by a negative 1. Okay, 1530. So if I were to have written out all the other terms there, whatever they are, and added all those up, I'd come out to 1530. So this is called summation notation, and it's just a short form of writing either geometric or arithmetic or really any kind of pattern or sequence. Here's just quick instructions on how to do that. If you wanted to try this one, that's a nice one. It's got fractions in it. Notice that it doesn't go on forever. It goes from 1 to 30, so I can't be using this formula. And I'm looking for a sum, so I'm probably going to be looking for that formula. But I need to plug a 1 in, then figure out what my first term was. Plug a 2 in, figure out what my next term was. I think it'd be 9th, 5 over 3, I think, plus, and just keep going, and then use my sum formula. Here's one last question. Same kind of thing, 1 to 8, or is that the one we did already? Oh no, it's similar to the one we did, but you can try that one. That's summation notation. Okay, hopefully that helps you with the geometric sequences and series.